Verification and usage of Leibniz Rule. In this video, we are going to verify that the nth derivative of f of x g of x, which nth derivative will be the sum, the sum of NCR, rth derivative of f of x, and n minus rth derivative of g of x. So let's start with a function. Let's say we have f of x g of x, and let's find its second derivative. Let us find by ourselves and then use the formula first. So first of all, for second derivative, let's find the first derivative. First derivative will be f of x times g dash of x plus g of x times f dash of x. Now again we need to find its derivative as well, because we have to find second derivative. Now again, if we have to find derivative, let's find derivative of this first. That will be f of x times g double dash of x plus g dash x times f double dash of x. Similarly, over here, that will be g of x g dash x times f dash x plus g of x times f double dash of x using product rule. Now this gives us f of x g second derivative of x plus 2 times, okay, this is not double dash, this is g dash x and f dash x, not double dash, sorry, 2 times f dash x g dash x plus g of x times f double dash of x. Okay, this is how we find out by doing by our hand, by just doing all the process. Now even if you use the formula also, it gives the same result. What formula says is, if you have to find second derivative, we will have a 2c0, 2c1, 2c2, and we will start for f of x from the from 0. So we will have f of 0th derivative is nothing, just the initial function, in the first derivative, in the second derivative, from this formula, and g starts from the last. Okay, so we will have 2 minus 2, that's 0 derivative, so 0th derivative is initial function itself, and the first derivative and the second derivative. So it works, okay. Now we just add them. Now this is just 2c0 is 1 itself, so that's f of x times g double derivative of x, and 2c1 is just 2, f dash x g dash x, and 2c2 is just 1, so f double dash x g of x. So we actually verified the formula for n equals to 2. Now if you want to verify this for n equals to 3, and let's do that as well, and then we will move on to some usages. Let's verify this for 3. So for 3, we just have to take derivative of the second derivative, and that gives us, so for this we will have f of x times third derivative of g plus second derivative of g times first derivative of f, and then from this we will have 2 times second derivative of f, and then 2 times first derivative of f and second derivative of g, and from last first derivative of g, second derivative of f, and then no derivative of g, third derivative of f. So if we add this, what do we get? Let's see. We get first f of x times third derivative of g, and then we get this is, so these two can be added, this and this. That gives us 3 times first derivative of f, second derivative of g, and if we add this and this, we get 3 times first derivative of g, second derivative of f, and this gives us g times third derivative of f. So this is by manually doing. Now if we use formula, what will you get? So f of x, g of x, third derivative. So we will have 3c0, 3c1, 3c2, 3c3, and f will start from this way. Zeroth derivative is in initial function itself, first derivative, second derivative, third derivative, and g starts from this way. No derivative, first derivative, second derivative, third derivative. Just add them. Now this is just 1, this is 3, 3c1 is 3, 3c2 is also 3, and this is 1. Now you can see that these are same. 1 times f of x, third derivative of g of x, plus 3 times f dash x, g 2x, 3 times f2x, g 1x, plus 1 times f3x, g x. So these are actually same, and so we have verified this. And I think you can also prove this by induction now, because we are just adding layer upon layer. So this should be possible to be proven by induction. And I do want you to try that. I don't think that would be a hard task, to prove using induction. I also think that we can also do it right now. But so let's try. Let's try. I'm not really prepared for that, but let's try proving this using induction. So for when n equals to 1, it holds true. Okay, so for n equals first derivative is just it's just f of x, g of x. Is it? No, it's not first derivative f, g. Okay, so it's something like this. And does this hold true? If we use the formula, this is 1c0, and for f of x there will be nothing, and over 1c1 we will have f derivative, and here g will have nothing, and we will have here derivative. So it's true. For 1 it's true. Now let's do it for k. Okay, look for a kth derivative. For kth derivative, let's say this was true. kc0, f of x, g of nx. And so okay, so for k this will be k itself, not n. And then kc1, f of x, f1 of x, g of k minus 1x. And then similarly for this will be, let's go to 2 as well, f2x, g of k minus 2x. It goes in a similar fashion up to k minus 1, that will be f of k minus 1x, or g1 of x, and the last will be kck, f of kx, and then g of x. Okay, now after this we need to find f of x, g of x to the power k plus 1. So that means we need to take the derivative of this whole expression and prove that this is actually equals to r equals to 0 to k plus 1. K plus 1 c r, and then f of r to the power x, and g of k plus 1 minus r of x. We need to prove this fact now. So let's take the derivative of this expression. What will we get? We will get kc0, and then f of x, g of k plus 1x, plus kc0, that will be f dash x, and then g of kx. Yeah, again for second term let us do the same thing. That will give us kc1 f dash x, that will be g of kx, and then kc1, that will be f double dash of x, g of k minus 1 x. For third, we will have kc2, that is f double, that let's say 2 of x, and then g of k minus 1 x, plus, and then over here there is something I don't know, let me not try, you can ignore them. Yeah, and then similarly for this one we have k minus 1, this is what will that be? What will that be? So f of like f of k minus 1, okay, so that f of kx, and then g double dash of x, yeah, and then plus, so okay, so not this, not only this thing, so we have taken derivative for f, so not for g, so okay, this is also 1, and then let's not take for k, let's take for g first. So let's take for g first, and then now let's do for k, and so that will be f of kx, g dash of x. Yeah, and now for the last term, that will be kck, and then that is f of kx, g dash of x, and then the other one will be kck, then f of k plus 1 x, and g of x. Okay, now this is the expression that we got. Now we will have, okay, so the first one can be written as kc0 is same as k plus 1 c0. Yeah, and we can write this like this, write other things as usual. Now you can notice that for second and third we have the same variables, f dash x, g kx, and also f dash x, g to the power kx. So these are same, so we can add their coefficient kc0 and kc1, and this is actually equals to k plus 1 c1. Yeah, so this is one of the like preliminary things in combinatorics. Most of you should have known in your high school classes this property. Yeah, so if you use this property, this will be k plus 1 c1. Yeah, so let's use that, and that gives us k plus 1 c1 and f dash x and g of k x. And similarly in next one as well, kc1 and kc2 will be k plus 1 c2, k plus 1 c2 f2x g of k minus 1 x. And similarly we can go, similarly it goes on, and over here we can see that this term will correspond with this over here, because this did with this, this did with this, so similarly these two will correspond. That's why I was stuck, like I was just trying to maintain the pattern, so I got stuck over some time over here. Now this sum will be k plus 1 ck. Yeah, and then we have f to the power k x, and then g dash x, and the last one kck can be written as k plus 1 ck as well, because the values are equal. Yeah, just like here the values are equal, so that's why we are substituting that, and that will be f of k plus 1 x, and then g of x. Now this is just the sum that we wanted. This is just the sum from r equals to 0 to k plus 1. Yeah, and there's k plus 1 cr. Yeah, and we have f of rx and g of, we just have the same thing, k plus 1 minus r. Huh? Here's k plus 1 minus 0, k plus 1 minus 1, k plus 1 minus 2. Yeah, so Oh yeah, we have proved. Yeah. Okay, so now this induction has already proved, and how induction works is we have seen for the base case one, and we assume that our case for k is true, and then we proved for k plus one, and because we proved for k plus one, the because we have proved for k plus one, now by principle of mathematical induction, this is proved for all k. Proved for all k, that means for all natural numbers. So this is the proof. Actually, I just wanted to verify it, but on the way I got motivated for a proof as well. And so this is the proof. Now, after we have this proof, now let us use this rule to solve some nice problems. So one of the problem that I have over here is this. Let's use Leibniz rule to prove this: x to the power 5, e to the power x, and then fourth derivative. So you know what to do: for c0, for c1, for c2, for c3, for c4, and for x to the power 5, keep putting from here: x to the power 5, 5x to the power 4, or 20x cube, 60x square, and then 120x. E to the power x from here, e to the power x, this will be just same, e to the power x, e to the power x, e to the power x, e to the power x. Now just add them, that is the answer. I didn't have a space, so I just wrote it down. I hope you understand this. So this is the answer. Quite easier, yeah? Now if you have tried the answer in a neat way, this will be x to the power 5 to c to the power x. This is 4 times 5 is 20. 20 x to the power 4 times c to the power x. 20 times, this is 4, 3 by 2, 2 6, 120. 120 x cube e to the power x. This is 60 into, this is 6, yeah? No, this is 4. 60 into 4, 240. 240 x square e to the power x. This is 120 into 1. This is 120 x e to the power x. So this is the answer. And Leibniz rule made it a lot easier. Otherwise, we have to find first derivative, second derivative, third derivative, fourth derivative. That will be a lot harder. Yeah. Let's go to the next problem. Now, the next problem is like this. Sine x, and then x to the power 4 plus 1. Now third derivative. Let's use the Leibniz rule again. So 3c0, 3c1, 3c2, 3c3. Derivative of sine. First of all, no derivative. First derivative, second derivative, and then third derivative, and another from back: x to the power 4 plus 1, 4x cube, or 2lx square, or 24x. Yeah, 2x square, 24x. Now just add this, and this is the answer. Yeah, hope you enjoyed these two problems, and hope you enjoyed the verification, and hope you enjoyed the proof that I was motivated during the verification. Actually, I wasn't planning to do, and I didn't like instantly had the proof in mind while I was making the video, so I just wrote the verification. But while doing the verification, the proof hit in my mind, and yeah. So it's just like if you are trying something, you might discover something new. So just try and do stops. Yeah, and hope you enjoyed the video. Thanks for watching, and look forward to seeing you in the next videos. And also, do check other videos in this playlist where I'm introducing some standard integration techniques or derivation techniques like this. Yeah, I will share the link of playlist over here in the tab, and there are other amazing videos like this. Thanks for watching, and look forward to seeing you in the next video.